Hello everyone. I had a couple of students ask about this question. It's on the exponential models uh, assignment or section 4.7, however you care to label it. So this is question 5 where we have the number of polio cases over a given number of years. This is actually kind of exciting because I do believe in my lifetime, we are going to eradicate polio. So we are very, very close to doing it, and the data here seems to be somewhat accurate when we're going through it. But essentially what we're looking at here is here's the year, and this is how many. The key part, one of the things that I've noticed students have missed the most, is this is in the thousands, so it's not like there are only 350 or 350,000 people that have polio. So when we translate this over, we want to make sure that our years are the number of years since 1980. So 1988 is 350. And then 1992 is 12. I've gone ahead and done that here in Desmos. If you don't know how to do that, that's totally fine. I can show you very quickly how to do that. So if I were to go in here, I want to hit this little plus sign, and then I want to choose table. What you want to really notice is the subscript here. So this isn't just X, this is now X sub 3. So now I can plug in values, right? I can say like 0 goes to 2 and 1 goes to 29 and so on. But if I want to create a model off of this, then I need to use Y sub 3. Now Desmos is smart in that if you hit a number next to it, right, if it's to the right of it, it will know that you're going to make a subscript from it. Now the important thing here is that when you're creating an exponential model, you don't want to use the equal sign, because the equal sign is something that connects, it's static, so it connects one value to another value. So in this case, since we are referencing several values, in this case we have 2, we want to use this symbol here, which is a tilde. That's the fancy word for this little swoopy thing here. Now, if you are using your calculator, what you would do is here you would click on ABC, and the tilde is hiding right there. If you are instead using a computer, like I'm using a university laptop here, above the tab button, you'll see the tilde next to like the little quote button. It's next to the 1 key, if that's helpful. But you can see what I did here is I put in those values where, again, X is the number of years since 1980, and these are the values as you see them. So 350 means 350 goes there. Now, if I want to do an exponential model in on like a graphing calculator, like a TI, you would do the hint as it says here. You would choose to do the exponential regression, but in Desmos you have to write up what that is. So in this case, an exponential regression is a times b to the x. And since my table has x1 and y1s in it, then I need to put x sub 1 there, so it knows to do that. Now, the program Desmos is fairly sophisticated, so if you wanted it to manipulate the logarithm in such a way that it was translated, so if you were adding or subtracting values to it, then you could actually get this to do the work for you. In order to do that, you would click this little check mark right here. So notice that these values change, where I have a negative 95% match off of it. You can kind of see what it looks like here. It's kind of hard to see with it zoomed out the way it is, right? But if if I had left it without it, notice that that it doesn't quite like match what I want it to be. I want it to have this negative value in here. Okay, so so in this case, we are going to use that logarithmic mode in order to get that. Here's an example of the same thing as a linear equation. So instead of y equals mx plus b, we have the little tilde thing there. Now, what we're looking at are these r values. It's the correlation coefficient. It's essentially the grade for it. So how closely does it match? Well, if we can look at it, this red line has about an 85% match to it, right? So the way it does it is it looks at sophisticated formula that looks at the minimum sum of differences, the minimum amount of space between each of these data points and the line there. So you can imagine there are all kinds of lines you could kind of choose to to represent that data, but the best one would be the one that has the minimum amount of space on it. So you can see the difference here between what an 85% score is, see how like small little gaps are popping in there, compared to like a 95%, where it's like pretty much on the ball with it, right? So, so our very first question here, when it says, well, which one should it be? The answer is going to be exponential in this case, because it matches it a lot more. Now, I like these, but it's intended for those of you using graphing calculators, so specifically the TI 83 and 84s. So that'll certainly get you through that. But at this point, we are going to use Desmos's parameters here. And just a quick overview, when I plug in that exponential thing here, the things that aren't typically defined, like let's say A and B, those become the parameters down here, which are just it's a fancy way of saying the parameters are the different variables we're looking at. Okay, so so in this case, we need to define some A and we need to define some B in finite terms. And notice that I get this as my introductory, so 3,744.55. Let's see if I can remember that. 3,744.55. That's not too bad. Hopefully I got it. There we go. And then B is going to be this 0.7375. 0.7375. Yeah, hopefully that worked. And the next thing that's going to get you is I very much want to write an X down here, but now I'm programmed, right? I've been conditioned to look at the actual function value here, because in this program, if whatever its independent variable is here, that's what you need to have there. You want to go, so I did it without mentioning it here, but we want to make sure we get it to 4 decimal places. So, for example, if this rounded up, let's say this was going to round up to 0.7376, then I would want to do that. Right? So that's going to take care of these two pieces here. Now, the very next one, these next ones are all going to be applications of using that model. So if I were to do this, I can see off the graph that it's decreasing, right? So it's going downwards. It's doing the right thing. We want less polio cases in the world. So it is decreasing, and the important part is how we read this. So every year we go along, we'll have 73.75% of the cases we had the previous year. So if we had 100 cases one year, then we have 73 cases the next year. That's how that will work. So we don't lose an equal amount each time. That would make it linear. We're losing a percentage of it there. Now, if that's what we have remaining, the 73, the flip of it, right, this 26.25 in my case, is what it's decreasing by. So that's definitely a spot you could get stuck in. These next ones have to deal with inputs and outputs. Well, T is the number of years since 1980. So this 2020 bit here is going to be 40 years afterwards. So in terms of my function, right, it's really asking, well, when, how many cases do we have? I'm going to get rid of some of this. How many cases do we have when X is 2020 minus 1980, or 40 there, however you want to address that, right? So you can see Desmos kind of gives me the answer here. The important thing is that answer is in thousands. So if it helps, we won't have 0.01 cases of polio. That's not like someone's foot has polio, but the rest of them's fine. Right, so that's this many thousands. So by 2020, there should be about 19 cases left. I believe, if I remember right, from early last year, we had less than, we were down to like a couple thousand, maybe even it was to the hundreds. But we were well within it. So America like pulling out of of funding the World Health Organization was one of the things that was prohibiting that from occurring. But I digress. This is what we're really wanting to translate. We want to take 0.19 and we want to figure that out in terms of the thousands, which you can kind of see how we do that, right? We just move the decimal point over 3 places. So in this case, how many cases will there be? We're going to say 19, right? So, and that's what the little hint is there. So when will there be 1? Well, we're not going to look at 1 for our function because that's going to be 1,000 cases there. What we really want, ladies and gentlemen, is 0.001 because that's going to tell me when I have 1,000 or 1 case left in the world, which that would suck to be that 1 person in the world that still has polio. I know mathematically that's how it's going to work. It's still unfortunate that that's how it plays out. So, so can you do this old school way? Can you set this to be 0.001 equals your, let me see if I can move it down, this 3,400 business? Absolutely. But I would not wish that upon any of you. So yeah, you could do it like that, and you could solve this accordingly. Right? Notice that it gives you the exact same result here as what was there with just the blue line with it. Right? But again, the point of this course is to teach you the computation piece of it, sure, but also the concept, right? So how do you use this model now that you have it, right? What kind of predictions can you make on it? This is a 95% pretty good model. So if this continues to behave the way it does, then we can say with some high degree of certainty that yeah, this should be how it works. But what does it mean? So if we were to go in there and look at that 49.715, remember X is the number of years since 1980. So 49.715 plus 1980. I'm going to check one more time just because I want to make sure I have the right thing. There's 715. There we go. Doesn't really change it. So in the year 2029.715 means it's going to be a little over halfway in the year, so maybe August, or maybe September of 2029. But certainly in the year 2029 is when that's going to happen. And this last one is going to be when is there going to be the half-life of it. So again, Desmos is intuitive. So if you talk about some variable a, then it's going to keep thinking of a as this 3,400 here. So when it asks, well, what's the half-life of it? This is our initial amount. So when we are first looking at this in 1980, we have what would this be? 3,744,000. 3,744,055,000 cases there. Is that right? No, 550. Son of a biscuit. 3,744,550 cases in there. Right? So that's what this thing means. So we want to know, well, when do we get to half of that? That's what we care about now. So so if we look at that, we again see that we're going to get there approximately 2 years afterwards, which is hitting a little too close to home for me because that's going to be in 1982 with it. So what happened with it? So what did I say? 2029. If you look at it, it looks like maybe I should jump it up. Yeah, let me jump it up. So you can see that it can be a little finicky. Let's see if that's part that makes that happy. Yep, it does. If I click on it, yeah, it rounds it up. So what's the thing to learn from here? When it's a decimal like this, if it's going to round it to the nearest year is what I think is going to happen there. And then here in 1982, let's see what happens. This is 2.2. That should work. So let me try 1981. Maybe it just doesn't like that. Well, you can see even with that in play, it may have some slight issues with it. But I hope that in terms of figuring out what it is, let's see what it's actually doing. Oh, well, that's dumb. How many years is it going to be? That's the 2.3 in there. So clearly I should have practiced a little bit more is what we're saying, right? So I should have rounded this thing off. I should have gone 2.277 and not made it the year 1982. Well, there you go, ladies and gentlemen. I'm not going to re-record this. I think it's valuable for you to see me make mistakes too, and know that this problem is inherently frustrating. So I hope, at a bare minimum, that it was helpful. By all means, if there are any questions, please let me know. I sincerely want to help. All right, have a great day.